introduction. So today I'm going to present our work, Gryphes, hybrid proofs for modular SNARKs with applications to zkRollups. So to start with, I will give some background about SNARKs, and thanks for the three previous introductions, the three talks, and we already know something about SNARKs. So SNARKs is about a succinct non-interactive argument of knowledge, and it allows the prover to prove the correct execution of a computation with a short proof to a verifier. And SNARK already for numerous applications, including the three talks we just heard. And today, I'm going to focus on the blockchain zkRollups and decentralized exchange. So SNARK usually encode computations into arithmetic circuits, and then further encoded into a discrete system. And SNARKs can handle any computations, but they cannot handle the if and else conditions efficiently. Because if you have if and else conditions, you have to encode both conditions into the SNARK circuit, and the prover has to go over both cases. Therefore, he has to pay twice the cost as a standalone circuit. And another case that you can also try to put two circuits for two conditions, but that will lead to two proving keys and two verification keys, leading to a more overhead for both the prover and the verifier. Therefore, one if and else is manageable, but thousands of if and else is not, and that is a challenge we are going to solve. And you will see a real-world example why we care about this special case. And we will take the example of decentralized exchange in the zkRollups, and we will first see how it works. So in zkRollups, users have many transactions, and they will post their transactions into a clear time group, and they will build a sequencer to check those transactions and execute these transactions. And the sequencer will update the space and have a new digest, and only post the digest to a layer 1 blockchain. And there will be another prover to prove these transactions are correct, and then going to have post this proof to validate this digest. And clearly, this model saves the storage of the layer 1 blockchain and supports more rich functionalities for the transactions. But for decentralized exchange, the burden will be on the prover because the prover needs to prove lots of things. And let's see what we need to prove. So for very basic operations, the prover needs to prove that deposit, transfer, exchange, and withdraw for the decentralized exchange. And for application-rich exchanges, there will be hundreds of cryptocurrencies, and there are various trading models, including spot trading, perpetual trading, futures, limit, and other trading, etc. Therefore, each user only submit one transaction, but proving circuit must include every possible operations the exchange must pass. And let's see how the people solve this problem in the real world. And we will consider the solutions in two angles: the supported functionalities and the proving efficiencies. And the most basic version is directly using the smartphone arithmetic circuit. And one example is a loopring project. It only supports very basic operations. And another project is called SNARKs for RAMs and zkVMs. So basically, they simulate the RAM operations into the SNARK and introduce another level of abstractions. So they have a very good support for even else or switch case conditions, but they have a high overhead for all the operations. There is another technique called SNARKs plus matrix lookup, which is proposed by Blanc, also in past 2 years ago here. So they encode all the possible circuits into a lookup table, and when the prover want to prove the corresponding circuit, they use a lookup. But based on our benchmark, the matrix lookup is still around 20 times slower than the SNARKs for arithmetic circuit. So the natural question arises that can we do something better? And can we achieve both the flexible functionalities and the efficient proving? And here's our result. So our first contribution is Gryphes framework for Pappas. So it proves the different parts of the computation using the most suitable SNARK for each part. And it directly have applications for zkRollups So we can support thousands of transaction types, and we achieve 11 transactions per second on the local server. And of course, it has um, uh, application, applications for Snark competitions. For example, the verifiable credentials or the IDs. And secondly, we have a link protocol for commit and prove snarks, or CP snarks, based on Huang, which is another popular snark. It achieves a quasi-linear prover, constant size proofs, and constant time verification, which is very important for the zkRollups scenarios. And it has efficient heterogeneous snark compositions applications because it provides the key building blocks for connecting Planck plus matrix lookups with vector-based CP snarks, for example, the growth systems. And we also have the open source all our components, including the CP snarks, matrix lookups, and zkRollups. So how do we achieve this? Our first observation is a matrix lookup or sub-Planck is still 9 times slower than Planck. So even if it transports edge cases, but it's not as efficient as we want. And our second observation is that in the real-world applications, this application usually contains two parts of computations: the lightweight application logic and the heavy shared crypto logic. In the shared crypto logic, usually every transaction has signatures. We have accumulator verifications like RC accumulators or Merkle trees, and usually the circuit needs to check lots of hashes. And this basically fits for all the transactions. And we will use another matrix lookup to handle the application logic so that it can handle the if analysis efficiently. And then we will have the link protocol to link them together to show they have to complete the transaction logic. And here are our experimental results. So we test our experiments with a server with 4 cores and 128 gigabytes of memory. So we consider 16,000 users in the system. We aim to support 1,000 transaction types, and the batch of proof contains 1,000 transactions per proof. And here is our result. So for the logic prover, it can handle the dynamic application logic and takes 46 seconds, about 50% of the total running time. For the crypto prover, we are based on growth testing, and it checks signatures and crypto updates, and it runs for 44 seconds, which is 48% of the total time. And to link them together, it only takes 1.9 seconds, which is only 2% of the total time, which is almost negligible, because in this way we cannot use the most suitable snark to prove the corresponding logic, and the overhead is only this linking proof, which is only 2% of the total time. And in overall, the proof takes 92 seconds, which we achieve 11 TPS on this server. So in conclusion, we designed Gryphes, a hybrid snark framework that separates the dynamic application logic from the fixed crypto operations. And we developed a link protocol for compose different proof systems together with only 2% of additional proving time. And our zkRollups types support 1,000 transaction types or even more. And it can achieve 11 TPS on our 4-core CPUs. And we have open source our code and benchmarks in this link. And please come to me to the poster session if you have any questions. Thank you.